And welcome back to the Simpkins Physics Corner. Man, it's been a minute, but let's get in on some AP Physics rapid fire for your rotational motion practice problem. So here we go. All right, we have a skater spinning at this rate with the rotational inertia of this when her arms are extended. What's her angular velocity after she pulls her arms in and reduces her rotational inertia to this? Well, when a skater has their arms out, they have a certain amount of angular momentum, and when they pull their arms in, they have a different amount of angular momentum. Well, I shouldn't say different. I should say it manifests itself differently, right? So the initial I omega is going to be equal to the final I omega. And so if the initial spinning rate here is 14.3 radians per second, and the rotational inertia initially is 2.58 and a bunch of units, then that is going to be equal to whatever 1.6 kilogram meters squared times omega final. That should be an F right there, by the way, what omega final is. Okay, so this is the law of conservation of angular momentum, which states that in the absence of a net external torque, the angular momentum of a system has to remain the same. Before and after has to be the same number. And so we see if we pull our arms in, we know we're going to spin faster intuitively based on our classroom discussions. But here is going to be our final rotational speed for the skater after she pulls her arms in. Not so bad. Let's look at another one. The centrifuge has a rotational inertia of this. How much energy must be supplied to bring it from rest to this speed? And it gives it RPMs, but why don't we keep it in rads per second because we like that. So the initial omega is 0, of course, and the final omega is going to be 430 radians per second. Now we have this I equal to 8.08 times 10 to the negative 3 kilogram meters squared. How much energy? So if you're spinning something, you're changing its kinetic energy. And when work is done, energy changes. Now let's think about the rotational version of work, if you will, right? Or actually, we can just look at this. We can say that's going to be the final kinetic energy minus the initial kinetic energy. And so the final kinetic energy is going to be made up of 1/2 I omega squared minus, and it was at rest at the beginning, so it didn't have any kinetic energy at the beginning at all. And so really this problem becomes pretty simple as long as we're careful about the way we do this. So 8.08 times 10 to the negative 3 kilogram meters squared, and this is our final right here, our final radians per second, or 430 radians per second, but that gets squared, and of course there's no kinetic energy initially, so the overall change in kinetic energy would just be equal to the product of those three quantities. So let's go ahead and throw it in. 5 times 8.08 times 10 to the negative 3 times 430 squared, and that's going to get us a change in kinetic energy. How much energy must be supplied? 813.56 joules of kinetic energy must be supplied. So not so bad for that one either. Let's look at the next one. A turntable of mass this has a radius of this and spins with a frequency of this. What's its angular momentum? Assume the turntable is a uniform disk. So I will always give you the I equation, specifically with the coefficient out front of it, on a test, but we do know that a disk has the I of 1/2 mr squared. We've seen a few of those. And so since we know that information, why don't we go ahead and find this real quick. This is 4.5 kilograms for mass, 0.077 meters for the radius, but that gets squared. And so we're going to go 0.5 times 4.5 times 0.077 squared. And that's going to get us an I of 0.0133 kilogram meters squared for our I. Now let's see what it's asking us. It says, what is its angular momentum? If you look at your equation sheet, angular momentum is I omega. And so really, we already just got I here, right? So 0.033 kilogram meters squared. And that's going to be times omega. Now, this is in revs per second, so just a quick little wave of the hand here. If we have revolutions per second, then in order to convert that, revs are on top, we want them to show up on the bottom, and 1 revolution happens to be equal to 2 pi radians. So this is actually solving for omega now, and if we multiply 0.536 times 2 pi, we have our new omega of 3.37 radians per second. So that's going to go right there into for our omega, 3.37 radians per second. And if we multiply that number, come on back, multiply that number by 0.0133, then we're looking at an angular momentum of 0.045 And there's a whole bunch of units going on there. What is that? Kilogram, meters squared, radians kind of go away per second. Okay, so there it is. Awesome, that's our L, our angular momentum for that disk. How about this one? It gives us the angular momentum right there. After application of a constant braking torque for this much time, it slows and has a new angular momentum of this. What is the torque applied? So this is Newton's second law, but the rotational version is that a torque applied is going to cause, well, we could do that, except it also has to do with angular momentum, which is L. And it turns out that a change in angular momentum will be resulting from a torque times a time. Okay, this is like the momentum impulse theorem, but the rotational version, right? This is momentum, this is a rotational impulse over here. So let's see if we can make this work for us. We do know the time, 2.1 seconds, so that goes there. And it says, what is the torque? So we're not sure about that yet, but delta L is simply L final minus L initial. So if we come over here, looks like our L final was 118, and our L initial was 246. And should I write units? Yes, but I'm not going to for the sake of time. Okay, so there's that. We divide both sides by 2.1, and that'll get us our torque. Now you notice it's a negative torque, and that makes sense because we had a decrease in angular momentum. So of course we have to have a negative torque. But let me go ahead and drop this in. That's not the number I wanted to type in. 118 minus 246, there we go. And then divided by 2.1 is going to get us a torque of negative 60.95 Newton meters. So that is the torque applied there in that situation. A diver can change his rotational inertia by drawing his legs. All right, so they're going to leave. They're going to pull himself into a ball and make 2 rotations, okay, in 1.25 seconds. So that's like the tucked position. The rotational inertia decreases by a factor of that. So the rotational inertia is going to go down by a factor of 2.99 when he goes from the straight to the tucked position. Okay, what was his angular velocity when he left the diving board? So this information right here, we have 2 revolutions in a 1.25 seconds. That's like the peak fast spin speed after he tucked, and that's going to give us, well, actually, hold on, let's change that to radians per second. So we're in omega land here. So we have revs on the bottom, radians on the top, and it's going to be 2 times 2 pi, if we multiply all the numerators together, divided by 1.25, and that's going to be 10.05 radians per second. So that's our omega final, if we call that the omega after the tuck. Now, this is not telling us what the I is, but it's saying by how much the I changed. So the concept here is that the initial angular momentum is equal to the final angular momentum. And so if we analyze this a little bit and we say, okay, well, here's what angular momentum depends on, and we happen to know what this omega was over here. Let's see, it says, what was his angular velocity when he left the diving board? So the angular velocity afterwards was 10.05 radians per second. Okay, and as you can see, everything is very linear. It's very straightforward. There's no squares, there's no square roots, there's no coefficient. It's just I omega equals I omega. Well, what does that mean? That means if I in the tucking process decreased my I by 2.99, that means that my omega experienced a similar increase by a factor of 2.99. Well, what does that mean? That means that my initial omega then was whatever 10.05 divided by 2.99 is. So let's see what that is. Divided by 2.99. I have a feeling it's going to be a nice number here. Okay, let's see. 3.36 radians per second. Just a quick sanity check. If you plug that back in over here, 3.36 radians per second, okay, and we call this I, well, it decreased by a factor of 2.99. So really you could check it by saying, okay, it was 2.99. Now it decreased to that factor of 1. And so that factor change there is going to give us our final result here for the spinning speed beforehand. Spinning flywheel has a rotational inertia of I. If the angular velocity decreases from this to 0 and that due to friction, what's the frictional torque acting? So let's see what pieces we have. It looks like we have some I, it looks like we have some omega, and it looks like it's asking us for torque. All right, so how do these things tie together? Well, it looks like we have the I and the omega already, which is related to L, and we know that a change in L is going to be caused by a torque times time. Let's see if we can maybe leverage that one. What is the frictional torque acting? Now, the change in L would be a result in the change in this guy over here, but you know what? I think we can solve for the change in L directly, because L is going to be, I should say the change in L is going to be L final minus L initial, which is going to be, it looks like the final is 0 because we stopped spinning. And then this part's going to be I omega because that's our definition for L angular momentum. So we have 364 for the I, and the omega is 43.1. And so our delta L here is actually a negative, which again makes sense because we have a frictional torque causing that change in angular momentum. And holy buckets, that's a large number. Let's see, did I miss something here? I feel like I'm missing something. I'm not. That's a really big change in angular momentum. All right, so 15,688 is going to be a very large change in angular momentum. All right, but we could bring that back to this equation, which is the angular momentum impulse equation, if you will. And so delta L equals torque times time. So we have this huge number, negative 15,688 equals torque times, okay, well, it was over 228 seconds, so it took a while. So that's good news because it's going to make this number a little less obnoxious here, 228, and our final net torque then would be the 68 here, 68.8 Newton meters of torque. Okay, so you really have to be able to juggle all these things. It's all about what you're given, you know, because sometimes you can get angular momentum from I omega, sometimes you can get angular momentum from torque time, sometimes you have to use both. How about this one? We're on a seesaw, a distance of, let's see, I'll put them over here just for kicks and giggles here, 1.7 meters, and that person is over here, and they have a mass of 39.7 kilograms. And so it says on a horizontal seesaw, what's the magnitude of the torque on the axis due to the weight of the child? Oh, good Lord, that's an easy one. So torque is Fr sine theta. The sine theta, remember, is the angle direction between the lever arm and the force, which in this case is 90 degrees. You can see that 90 there. So the sine of 90 is at 1, so that just kind of goes away. And so the force, what force is being exerted? It's the force of gravity on the kid. So this turns into mg, that turns into r. So this turns into 39.7 times 9.8 times whatever the radius is, 1.7 meters, to get us our grand torque over here. So let's see how that works out. We have 39.7 times 9.8 times 1.7. 661 Newton meters of torque for that one. Not so bad at all. Okay, that's it. We got to the end here of our rotational ones. There is a little one with a plank at the end of the practice set, but that is rotational equilibrium, which we'll touch on a little bit later. It will not be on the quiz that's coming up here. So until next time, it's Mr. Simpkins in the Simpkins Physics Corner, keeping your L's and your torques with the time and the, yeah, that didn't work. I'm done. It'd be great if I could start this recording. Well, once upon a time, there was a physics teacher who was making videos in the morning, and the screencast-o-matic wouldn't let him hit the pause button. So he was stuck in an infinite loop of recording video until he could magically make his way down to the bottom of the screen.